Welcome to a new unit. Unit 6 is called Discrete Math. Discrete math is not like it's secret or something. Discrete is basically a type of math that is not really as algebraic or continuous, and we'll talk about what it means in a minute. And our first day is going to be about sequences. So what is discrete math? Discrete math is a branch of mathematics that deals with topics that only have distinct separated values. So the idea is that what we have are going to be things such as a first term, a second term, a third term, etc., and nothing in between. So between your second term and third term, there's no 2.2 term. And when we graph something like this, and we'll get to that later, it's going to be very separate and distinct values, not connected at all. Very distinct. As opposed to what have we been studying all year? Well, we've been studying functions all year, and everything we've been doing has been continuous math. In other words, f of 1, f of 1.2, f of 2.7, and everything in between. Very continuous. Maybe graphs that maybe look like this. And the type of functions we've been looking at all year have either been power functions, rational functions, trig functions, exponential functions, and lately we've been looking at log functions. So that's the difference. Very continuous looking graphs, very much any values that we want. F of negative 8.6. Who cares? F of pi. Discrete math, there's no such thing as f of negative 8. You can't have a negative fifth term, and so on and so forth. Let's go on to the next. We've got to grab. I'm going to flip it up. And grab this. So what we're going to study today is going to be a sequence. And an example of a sequence of numbers are 5, 10, 15, 20, 25, 30. Or we can do 3, 6, 12, 24, 48, 96. These are just sequence of numbers. Is there a pattern to these numbers? Well, for my example, yes. I'm adding 5. And for the second pattern, the answer is yes. I'm multiplying by 2. Well, maybe there's a pattern. Not only is there a pattern, but maybe there's a formula for all this. Well, let's see what we got. Well, for this one, maybe I would do something like y equals 5n. Notice I'm going to use n instead of x. And because we're going to use whole numbers like 1, 2, 3, 4, no decimals. But we're going to work on new notation today. This is the key. Instead of calling y equals, we're going to call it a subscript n equals 5 times n. This new notation is going to be the key. That's when we're going to use letters with subscripts. And for this one, maybe this pattern would be y equals 3, 2 to the n minus 1. And we'll talk about how we get to that. It's not important. Or maybe we call it g sub n is equal to 3, 2 to the n minus 1 again, using this new notation. This is going to be the key to today's lesson, is understanding what this notation is. We're not going to call things y equals or f of x equals. We're going to use this special notation, a sub n, g sub n, or some other letter with a subscript. So how many terms did both these sequences have? Both had 6 terms. But But there could have been more terms or there could have been less terms. It's not really defined. Is the number of terms limited? The number of terms could be limited or they could be unlimited. It all depends on what we have, and we'll talk about what that means in a minute. So there's two types of sequences, finite and infinite. Finite is a set number of terms, and infinite is a unlimited amount of terms or number of terms. So my first example of 5, 10, 15, 20, 25, 30, this is a finite sequence because it just has 6 terms. Well, I modified that other example of 3, 6, 12, 24, and then I did comma, dot, dot, dot. This indicates that the sequence goes on forever. It is unlimited. Dot, dot, dot with no ending. Okay, so a sequence is just an order list of numbers. There could be a pattern to the numbers, or there could not be a pattern to the numbers. And each individual number in that list is called a term. First term, second term, third term, 8th term, 100th term, whatever you have. You could have a finite sequence. There's only so many terms, like this one only has 6 terms. Or it could be an infinite sequence that it goes on forever by the dot, dot, dots. The key with sequences is its notation. It has a very special notation. It's just any letter you want with a subscript n, such as a sub n. The subscript n denotes the term. So a sub 1 is the first term, a sub 5 is the 5th term, and so on and so forth. So from this example here, sequence A sub n is just a way to call the sequence by its name. A sub n means sequence A. You have right here is the first term. Right here is the third term. And right here is the nth term. Since I don't have a number on it, it says nth term. But because this is a finite sequence, it's also the last term. Whatever that last term number, if there's only 10 terms, it would be a sub 10. But again, I could use any letter I want to name a sequence. This time I'm using a lowercase, b sub n. Use any letter I want. That's its name. Again, I have a first term. And this term right here is the nth term. It's unknown to me. It's an unknown term. There's more terms after it, but b sub n could be the whatever term I'm looking for. So let's talk about the way we do things. What term precedes b sub 30? Well, b sub 30 is the 30th term. So what comes before 30? 29. So b sub 29 is right before b sub 30. What is right before b sub 300? Well, what comes before 300? 299. So b sub 299 is right before b 300. And then finally, well, now we're going to get a little abstract. B sub n. What comes right before b sub n? Well, what did we do every single time? We subtracted 1. So right before this is b subscript n minus 1. And this stands for the previous term. B sub n minus 1 is right before b sub n. Okay, and that's what we're going to do things. So if I have a long list of terms, b sub 1, b sub 2, b sub 3, first term, second term, third term, b sub n minus 1 is the previous term, and b sub n is the new term that I'm looking for. And it's going to be important later. When we start doing this on a calculator, and we're going to do some things on a calculator today, calculator is going to be really important. Instead of calling it the previous term, it's going to be the A and S, which stands for answer. It's a special key in your calculator, and your calculator is kind of programmed to do all this stuff. It'll be a nice little trick that we're going to do. Okay, so we're looking at this sequence A sub n, and A sub n is a nice little finite sequence of 1, 4, 9, 16, and 25. There's only 5 terms. So when I ask what is A sub 1 and what is A sub 4, well, A sub 1 is the first term. According to this list, A sub 1 is equal to, the first term is 1, A sub 4 is the fourth term, and according to the sequence, A sub 4 is equal to 16. Now the question is there a pattern for the sequence? And we'll talk about it in a minute, and we'll try to figure out a formula, but yes, there's a special pattern. And then they ask a question, what is the 8th term? Well, currently, there is no A sub 8, 8th term. I only have 5 terms because A sub n is finite. Okay? But if I wanted to find the formula, what could be the formula for the sequence? Well, if I look carefully, it looks like they're just 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So A sub n is equal to n squared. Remember, we're not going to use x so much. We're going to use the letter n to represent like whole numbers. So if I wanted to find the 8th term, so if there were more terms, then A sub 8 would be 8 squared, which is just 64. Okay, if we wanted to find an 8th term. Okay, we're going to work on writing our own formulas right now, or looking at patterns. I want to make sure you understand that only letters can have a subscript. So A sub n, B sub n, T sub n, whatever you want to call it. Numbers do not. So there's no such thing as 5 subscript n. That is impossible to have. Numbers do not have subscripts. So the idea, there's one way to write things, is called an explicit formula. Explicit formula is just one equation, and I can determine each term from that equation, and it's an expression that it's a formula that you just uses the letter n as the variable. Okay? So when I want to find terms, I'm just going to plug in n. Okay? This is basically very similar to doing f of a number. If I say find f of 5, you plug in 5. Well, when I want to find the first term, I'm going to plug in 1. When I want to find the second term, I'm going to plug in 2. And so on and so forth. So an explicit formula is a very easy way to figure out the terms in a sequence, because all you're going to do is plug in a number. And you're going to plug in numbers like 1, 2, 3, 4, 5, or 10, or 1,000. You're never going to plug in 7.2 or 8.3 or pi or something else, because you can't do that with sequences. You only can plug in whole numbers. So for my example here, I have a nice sequence that says A sub n is equal to n squared minus 3, and I want to find the first 4 terms. So that means I'm going to plug in the numbers 1, 2, 3, and 4. So all I'm going to do to figure out the first, second, third, fourth term is plug a number in for n. So A sub 1, I'm going to use the number 1, 1 squared minus 3. A sub 2, 2 squared minus 3. A sub 3, 3 squared minus 3. And A sub 4 is going to be 4 squared minus 3. And I get negative 2, 1, oops, erase 6, and 13. So I could rewrite this all as, I could write them as A sub 1 is equal to negative 2, A sub 2 equals 1, A sub 3 equals 6, A sub 4 is 13, or the first 4 terms of A sub n are equal to terms negative 2, 1, 6, and 13. And those are my first 4 terms. Okay, and when I want to find, let's see if I can move this up. Won't let me move. Come on. When I want to find a sub 10 and a sub 30, all I have to do is plug in 10 and 30. A sub 10 is equal to 10 squared minus 3, which is 97. A sub 30 is equal to 30 squared minus 3. 30 squared is 900 minus 3 is 897. So I get a sub 10 is equal to 97. A sub 30 is equal to 897. And really, for an explicit formula, explicit is really easy. Just plug in n to find the nth term. Want to find the 102nd term? Just plug in 102. The recursive formula is actually a little bit harder to work through manually. We're going to show on the calculator too, but it's multiple equations based on a starting point. You need to know a starting point, and a pattern. And the idea is that it's called recursive because your last results that you just got will recur to refine the new result. So you're always using your last answer, your last result, the previous term, to find anything new. So the starting point is just really the first term, and the pattern is going to use the previous term, or what the calculator calls the answer. Okay? So that's the key. Now the notation here is a little bit more difficult. This is where people get thrown off. Is this r sub n minus 1? Is like, what does that mean? Well, that just means the previous term, and this is the variable of interest for us. That's what's going to change every single time, is that we're going to use that r sub n minus 1, or whatever letter we're using, n subscript n sub 1, doesn't mean subtract 1 from a number. It means use the last answer you got. So for an example, we are going to use this right here. I have a nice little pattern, and this, I'm going to circle it in gray. R sub n minus 1 just means the previous term. So if I wanted to rewrite this, this has 3 times my previous term plus 2. That means whatever my last answer is, multiply by 3 and add 2. So I want to find the first 4 terms, and I'll show you how I'm going to do that. Okay, I wrote all this out. So my first term, R1, is given, and R1 was equal to 5. That was given us right here. R2 is going to use that last answer of R1, so it's going to be 3 times R1, which is 5. I'm going to add 2 to that, and I get 17. So the idea is that it is using that last answer. That's what it says right here. 3 times the previous term plus 2. When I want to do R3, it's going to be 3 times that last term of 17 plus 2, which is 53. If you notice, it took that last term of 17 and plugged it in. And then R4, it's going to be 3 times that last answer of 53, add 2, which is 161. Again, it is taking that last answer and plugging it in. So that's the way it's going to be determined. I'm going to show you how we're going to do this on the calculator in a minute. But if I wanted to rewrite this, so the first 4 terms of sequence R sub n was 5, 17. Well, that's terrible. I'm not even paying attention. 5, 17, 53, and 161. Those are the first 4 terms. So I needed to know the previous term every single time to find that new term. I was always using that last result, plugging it in to the pattern that I had. to find the new result, and I repeat it again and again and again. So I'm going to show you how the calculator is built for all this. I don't have to do this much explicit work to figure this out. The calculator has a nice little repeat pattern that you could be built into it to figure this all out. And the way it's done is, first thing I'm going to do is type in R1 is equal to number and hit enter. Second thing I'm going to do, I'm going to type in the pattern. Where am I? I'm going to type in the pattern. I'm going to show you how to do that in a minute. And hit enter. That'll probably figure out my second term. And then I can just repeat enter. Because the calculator has a memory. The calculator remembers the pattern. As long as you don't change the pattern, what you develop in the calculator will remember that pattern that you developed. So on my calculator, I'm going to figure out how to do these two things, R sub 10 and R sub 30. Well, technically to R sub 10, I have to know all 9 terms before it, and R sub 30, I have to know all 29 terms in front of it. That's a lot of plugging into the calculator if I did it very much longhand. I'm going to show you how we do this on the calculator by following this guides in purple that I just did. Okay, so following what I said in purple is that what we're going to do, the first term, R sub 1 was equal to 5, enter. Now the pattern was times 3 plus 2. So one way to do it is just to hit times, because as soon as you hit times, it hits answer times 3 plus 2 all together in one line. Hit enter. And it says, okay, I'm taking my last answer times 3 plus 2. Second term was 17. And now you could just hit enter again, and it remembers that pattern. Now my calculator is new, it shows the pattern again. If you have a little bit older calculator, it just shows you 53. It doesn't show you answer times 3 plus 2. Another way to do it, 5, enter, and I could do 3 times, and the answer key is in blue above the little negative sign. So second negative sign plus 2, and now that really says 3 times my answer plus 2. The other one said answer times 3. Same thing. Enter. Enter. That's my third term. And now I just keep hitting enter, and I count every time I hit enter. So fourth term, which is, these were the first 4 terms, 5, 17, 53, 161, 5, 6, 7, 8, 9, 10. So the 10th term, R sub 10, is 118,097. And then we're going to do R sub 30 equals, I'm going to go back to my calculator. This is where you have to be careful. So we're on 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So that is 30 times. I was very careful to count. So I have R sub 30 is equal to 4.118 times 10 to the 14th power. That's what it said. I'm going to circle it for me, and there we go. And that's how I find those two terms. So now the ultimate question is, which is easier to find? A sub 100, the 100th term in the explicit formula, or R sub 100, the 100th term in the recursive formula? A sub 100 is much easier to find. All you got to do is plug in n equals 100. R sub 100, you technically need to know all 99 terms before it, and that means you got to, even if you did it on the calculator, that is hitting enter 99 times, making sure you hit it exactly right. You don't hit a missed finger, you don't do this, you don't do that. It's doable. I'm just saying, I wouldn't be so confident in it. So there's a very special pattern that's a recursive pattern called the Fibonacci sequence. Maybe you've heard of Fibonacci before, or maybe you didn't know how it was calculated. I'm going to show you how it's calculated. The Fibonacci sequence is each new term after the first 2 is the sum of the previous 2 terms. So the first 2 terms are given. The first 2 terms are 1 and 1. And then the new term is the sum of the previous 2. So I wrote out the first two terms. First two terms are 1 and 1, and the next new term will always be the sum of those two previous. Well, right now I only have 2, so 1 plus 1 is 2. The last two numbers are 1 and 2, they add up to 3. The last two numbers are 2 and 3, they add up to 5. 3 and 5, they add up to 8. 5 and 8 add up to 13. 8 and 13 add up to 21. And I can go on and on and on and on. And that is the Fibonacci sequence. A very special pattern. Happens in nature all the time. You can see the way the branches are splintering off. You can see the petals on the flower. There's just many ways in nature that occurs because, you know, math is nature, nature is math. So we're going to practice some problems. On number 1 and 2, we have explicit formulas where I have n is my variable, and I'm going to plug in, I want to find the first 4 terms. That means I'm going to plug in the numbers 1, 2, 3, and 4. I also want to find the 100th term, so I'm also going to plug in 100. And like I said, you could do this pretty much by hand, or you can use your calculator. We're going to use a calculator a lot for this unit, so don't be afraid to use your calculator. And I'm going to show you how we do all this. So the explicit is pretty easy. All I had to do was plug in the numbers 1, 2, 3, 4, and 100, and I did all this work. On the second one, because there's a fraction bar implied, if you just use the slash key on your calculator, you better put parentheses around your whole numerator. It's up to you, or you can use that special fraction key. If you need to know where that special fraction key is on your calculator, I will show you. But it's under the alpha, and then you go up to y equals, and is the very first one, and you get the fraction bar built into the problem. You don't have to worry about parentheses as much. But explicit are pretty darn easy. All you have to do is plug in the number. Now here's the recursive one. A recursive is going to be multiple equations. Explicit is going to be one equation where you just have n as the variable. The recursive is going to be multiple equation, usually 2, and r sub n minus 1 in this case is the variable. That's what's changing. That means the previous term. So r sub 1, which is given to me, is equal to 5. And I have to, when I do r sub 2, I have to do 3 times that last answer of 5. I get 15. R sub 3 is going to be 3 times that last answer of 15. I get 45. R sub 4 is going to be 3 times that last answer of 45. I get 135. And then I have to figure out all the way out to the 8th term because it says find the first 4 term and the 8th term. So I'm going to use my calculator to figure this out. So I have the calculator side by side the problem so we can see what we're doing. The first term is 5, so I'm going to hit 5 and enter, and there we go. And the pattern is 3 times my answer, or my answer times 3. So all I have to do is hit times 3. That's it. Don't do any more. That means take your last answer times 3, and I get 15. Now every time I hit enter, it remembers that pattern. Enter, enter. There's my first 4 terms, and look, I get exactly the same as I had before. And now if I want to find the 8th term, I'm already at the 4th term, so I'm going to have to hit enter 4 more times. 5, 6, 7, 8, and there is my 8th term. So you see for number 3 I completed, I got the first 4 terms and the 8th term. Number 4, it says t sub 1 is equal to negative 2. T sub 2 will be that last answer, negative 2 squared minus 3, which is equal to 1. T sub 3 is equal to that last answer, so 1 squared minus 3, which is negative 2. T sub 4 is equal to that last answer of negative 2 squared minus 3, which is 1. You can see I'm always using that last answer every single time. So my first 4 terms are negative 2, 1, negative 2, 1. Seems like I'm finding a pattern here. But I'm going to use my calculator to even find the 8th term. So if I want to do this on my calculator, which makes it very easy because the calculator has a memory, I type in the first term, which is negative 2, hit enter, and then it says square it minus 3, so I'm going to hit the squared key, which already puts the answer, minus 3. There's my second term, and now when I hit enter, that's my third term. When I hit enter, that's my fourth term, and look, those are my first 4 terms. I'm going to hit enter 4 more times to find my 5th, 6th, 7th, 8th term. But I had the conjecture the 8th term was going to be 1 because I'm seeing a pattern here. So I'm going to write all this out, and you can see all the terms. So I wrote it all out. You could see T1 is negative 2, T2 is 1, and I think all the T's with the odd subscript is equal to negative 2, and all the T's with an even subscript is equal to positive 1 if you pay attention to the pattern. And I made a funny pattern that does all that. It's not going to happen too often, but you see what we can do. Okay, that's day 1 of sequences.